So we'll talk about SVR, the three magic letters SVR, what 120 stands for. Simply Secure Vector Routing. Now, what is Secure Vector Routing? I think that's a big question. What 120 routing is really based off is sessions. That is, we are session oriented. For every single packet, we create sessions. So that's the basis on which 120 routing platform is built on. Now, for every session we create, we believe that it has to be secure. That's where the security piece comes. That is, whenever a packet is going from one 120 router to the other 120 router, it should be inherently secure. So the routers by default are not secure. So you have to have tunnels to encrypt. You can have IPsec, everything, any kind of encryption technology there. But we believe when a packet leaves a router, it has to be inherently secure. At the same time, we have to maintain sessions to have policies. We'll come into the details a little bit later. Then application-centric. Now, how does session awareness help us? Now, if you are session aware, we know what application you belong to. So automatically, you get the application awareness along with it. So security, the direction, the vector is the next piece. That is, applications are directional. That is, you're trying to access an application. The application is not trying to access you. Even if the application is trying to access you, that's a different direction. So directionality is an important piece. That's where the term vector comes in. So it's inherently secure. We create sessions. And we are directional. That's where the vector piece is there. So application and service-centric. And service, you already have heard about service in the previous session. What a service is, what a tenant is. We'll come to it again. Then routing without tunnels. Yes, we believe that when you send a packet, you have to be able to route the packet or forward the packet like IP packets. So you don't need to have any tunnels. You don't have to add any other fancy networking schemes. You simply send a packet from one router to the other, just like it was supposed to be. But unfortunately, that's not how the networking works right now for different reasons, for various reasons. Then zero trust security. We believe in security, 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 security. That's why SVR stands with secure vector routing. So zero trust security. We'll come to all these terms in details. But the basic premise is that the fundamental basis on which 120 does routing is different, is completely different from the way any other networking scheme you have seen. Why? Simply because we are sticking to the basics, that is, take a packet, NAT the packet, send it to the destination. It doesn't matter how it's been sent, but just send the packet to the destination. But with as much security you can get, as much session awareness you can get, and as much policies you can apply on it. So that's what secure vector routing is all about. So let's go over this again. So you can see a bunch of 120 routers. All these are 120 routers going from a source to a destination. Now, so when a packet flows from a source to a destination, we know it's a deterministic. That is, we need to know to make sure the paths it take are deterministic, the forward and the reverse. Now, why that's important is asymmetric routing. If you do not have the deterministic session awareness at every hop, it's possible you'll get a packet from a different route altogether, which is not desirable. We ensure that that doesn't happen because at every stage we have sessions created. We'll come again to a detail on how that session gets created across routers. Then security. As packets flow across each edge, each packet is encrypted as well as authenticated. Now that's an important piece. By default, we encrypt and authenticate the packet. So if you see the payload here, the payload is encrypted. The metadata is also encrypted. I'll come to what a metadata is. Now the basis of SVR is the first packet processing. So what is a first packet processing? Let's say a packet comes to a 120 router and it has to be sent out to another 120 router or sent to a particular application. We take the first packet and run it through a bunch of policies, figure out where it has to go, and then create a session for it. Now, if a packet is coming into a router, going out locally, it's like any other router. You have a fib. They may create flows. That's fine. Yes. But when it leaves a 120 router and goes to another 120 router, that's where the real benefit you get. Because what happens is we take a packet which has that payload, the one in blue. So this is the payload. Then what we do is we put something called metadata. Now, what is this metadata? The 5 tuples, the source IP, dest IP, source port, dest port, and the protocol, those are the 5 tuples which uniquely identify a packet coming in. That goes in the metadata. Then the tenancy, the service which it belongs to. For example, if a packet comes in and we define it's like tenant red, and then we say, okay, that tenant red has access to the web service because it's going to port 80, then those information, that will go into metadata. Now, why does it have to go into metadata? Because SVR relies on using the source IP of the first router and the destination IP of the next router to route the packets. That is simply how do you route it or forward it, send it to his destination. He can have multiple destinations, one destination, does not matter. All we are trying to do is take the packet from here, send it to the second guy. And what does he do? He takes the packet from here and sends it to this guy. So at the end of the day, when you have 2 routers, a router has a source IP, the other router has a destination IP. All we are saying is that's the transport. That's the underlaid transport, which could be anything. It could be the WAN, it could be a LAN, it does not matter. As long as 2 128 routers are there and they're reachable via IP, we simply IP forward the packet. Now, where the magic happens is actually in the metadata. So here, this metadata is there in every first packet. So when a packet comes in and goes across all the way to this destination, how do we maintain the session? That is via the metadata. Because at the end of the day, whatever magic you do, you have to do some kind of signaling. It could be out-of-band signaling, or it could be in-band signaling. So simply think of SVR as an in-band signaling mechanism where as the packet goes through, we carry the signaling information and keep it in every single router. Now, the beauty of this technique is you don't have to carry this metadata in every single packet. Why? Because the reverse packet will turn it off. So once the information is on all of the routers, and why the reverse packet is important is that tells us that the reverse packet has seen all these routers and has turned off metadata. So that's an assurance to us. It's like a signaling scheme. I've sent it to you, so you're sending me back ACK. So for TCP, it's simple. SYN packet goes through, SYN ACK comes through. For UDP, if there are reverse packets there, yes, it works. If there are no reverse packets, what we do is we have a metadata turn on packet, which we turn on a per session basis, which is configurable. It could be 10 packets, 20 packets, it does not matter. So at the end of the day, the first packet goes all the way to the destination, and then from the destination, we turn off the metadata, and then the flow is already set. So now if you look at it, after the first packet processing, there's a flow here, which is with the original 5 tuple. There's a flow here, which is with the WAN IPs. Let's say it's a WAN IP. There's a flow here, again, with the IPs between the routers. So the flows getting installed are simply the external IPs. That is your IP with which you're coming and the IP with which I am my local IP. Now, there could be CGNs in between. There could be NATs in between. It does not matter. Why does it matter? Because that's how the packets are coming in. Now, you could ask, OK, the CGNs can change. Let's say the IP changes. Does not matter. We detect if there are CGN changes, and we turn on metadata again to have it. So the beauty of our scheme is whenever the flows are set up end to end, you don't need the extra information to be carried. So if you're comparing this to a tunnel, which will come later on, the tunnel has an extra header which you're carrying, which is the information. And we have already carried that in the first packet. So you don't need to carry it anymore, and the flows will determine it.
How large is the metadata?
So the metadata could be around 150 bytes. About 150, 200. So you can add more stuff into the metadata depending on the features you have. So that's a good part. You can keep on extending it however you want. Let's say you want. So it's around that much would be the first packet metadata.
Right, and I'm assuming that we're going to have to adjust MSSIs because they're going to add that much into that payload, even though it's only in that first packet. We're still going to have to adjust. I mean, we'd have to do it with a tunnel anyway. That's not a big, not a big differentiator. But
so for TCP, if you think about it, it's a SYN ACK. So literally the SYN.
So you may not have to. You might be able to get away with it, but
right.
You'd be taking a risk if it was a full-size packet on the first. If it was a UDP packet,
yes,
yeah.
Correct.
Well, for UDP, we do our fabric fragment, which means they actually you wouldn't really need to take that into consideration. We'll take that into consideration.
Okay.
Yeah, so what we do is, so just to mitigate the fact that, so what happens is, well, we'll go to the details of Waypoint. There could be a lot of fragments, like you said, can happen. And you could even run into fragment ID collisions because of UN16. To mitigate that, what we've done is something called fabric fragmentation. That is, literally we take a packet, add the metadata. If it's beyond the size, we fragment them into separate chunks. So it'll see as 2 different 120T packets going through. Okay. So we put 2 metadata, packet 1 with metadata, packet 2 with the second metadata, and send it through. And those have fragment IDs in it, and we ourselves will essentially take it and convert to 1 packet and pretty much create it. So it's not the fragmentation of the normal IP fragmentation. We do fragmentation on our side just to mitigate this particular case.
Okay, so you guys have a mechanism for that. Do you guys honor DNF? If it's tagged DNF, do you still fragment it on the fabric, just out of curiosity?
So
it's not a fragment. It's an IP fragment.
Right.
Yeah.
It's got a header on it. It's got an IP and a transport header and everything.
So everybody else is seeing it as 2 normal packets.
Your frame's not a fragment.
Yeah, it's our fragmentation.
Okay, fair enough.
So from IP perspective, they don't see fragments. From our perspective, you see fragments. But yes, that's
okay.
So yeah, it's like the technical term where the fragment is IP fragment. No, but we fragment. Yes. So
Jordan, it's not a fragment from a certain point of view.
Yeah.
I don't care about the actual data. To us, we didn't fragment it at all. I don't know what you're talking about.
Right.
Well, that's feedback that doesn't have to go back to the originator of the packet, though.
Right.
It doesn't matter to him.
I mean, but there are
not honoring it makes sense in that case. Too.
Right, but there are applications where, I mean, and it's kind of ridiculous that it gets set most of the time, to be quite honest, but there are applications that do care about this, right, whether or not you fragment the data or not. I don't know if it would have adverse effect. I don't think it really would. I think they're mostly worried about out-of-order packet. We see it in voice a lot, right? So like that's where we typically see it. So long as you deliver it in order, I don't think it's going to matter, right? Yeah, so.
I mean, that's why the session orientation works. I mean, because every packet we are sending from the first router itself, we are sending it in order, and it will be received in order. So we don't have any, even for the fragmentation case, right? We have fragment IDs, so we wait for it, and then we reassemble it and send it across.
So we don't have to be inefficient with MTU, is what you're saying.
Yeah.
Yeah, awesome.
Right.
Can you talk a little bit about how you do the application identification on the first packet?
Okay, so application identification by itself, it's a bigger topic. I think it will be covered in the coming session. But how the identification happens is literally the 5 tuples. The 5 tuples are the identifier for a particular session. Now, that's at the layer 4, right? So let's say you create a service. And the service, at the end of the day, will boil down to IP address, protocol, and port, right? So when a packet comes in, I can draw it if you want. Essentially, we classify the packet. And how we classify the packet is, first thing is we assign tenancy to a packet. So the tenancy could be a network that it belongs to. It could be simply the VLAN on which it belongs to, or it could be simply the other router which says. That's a point I'll mention, because in SVR, once the ingress router has made the decision, you don't have to do anything else on the other router because he has already made the decision for you. So these are 3 things. It could be a network, it could be the ingress router which has decided the tenancy for you, in whichever way it is, or then it could be that interface VLAN. So the first thing we do is figure out what tenant you belong to. The moment once you have that, then you have to figure out what are the services allowed for this tenant. So tenant could be broader. Why I'm saying broader is in a moment, I'll explain why. So let's say you have a web service, you have a database service, and you have an internet service. So you have 3 services available. And you're going to port 80. So obviously you're going to hit the web service port 80. So now you get to the fib, which is the web service, where you hit, okay, port 80, I've got it, great. Now what do? Then you have a granular access policy. What that does is, now as I said, that's why I said tenant is broader. Tenant defines the network. Now I can say, hey, I don't want to let these users access the web. I only want to give it to maybe from .1 to .10. All the others, I don't want to. Or you can even define tenant, saying .1 to .10 is tenant red, .11 to .20 is tenant blue. I only want to give access to tenant reds. So you classify a broader set of tenants, find what service it has access to. So you hit the service. If it doesn't have access to any service, it'll get dropped. But let's say you hit the service. Once the service has been reached, then you find out does it have access? You go even more granular, say, does it have access? If it has access, then you go to the slow path for first packet processing. Otherwise, you just drop the packet. Now, as part of that, we also find out what policies can be applied to that service. Let's say it's a particular web service. It could be, let's say, best effort, or it could be the highest priority for TE. You can find that. Then you find out, okay, what are the path failure, what are the SLAs associated with it? What are the path failure techniques associated with it? So you figure out all those, because you don't have to figure out. The moment you hit the fib, we know what is associated with it. And you set up a flow and actions which correspond to those properties. Now, that's how a normal session gets identified. Now, for application identification, it's a different module, but I'll just touch upon that a bit. There are multiple schemes we do. One is a script-based scheme. So with a script-based scheme, what you could do is it's very flexible. You can create IPs and port combinations and say this particular name. Let's say I'm taking Microsoft as an example. So they have these IPs which are available where you can query and get the list of IPs. You can say Exchange are these set of IPs. This is for Office 365. Then Word are these set of IPs. So you have all those IPs there. So what we do is we consume them. We can put in the fib. When a packet comes in going there, then we say classify them as that. So you can see the counts of those applications. Then you can apply policies to those particular ones. That's one example. The second example is certificate. So we can also turn on the certificate feature where we parse the certificates and figure out what the domain names are. So you could even do a glob match, say star.google.com. I want everything to start. So we pass the certificate. We will find out, okay, this go in there. We can deny or accept it. So those are. I'm just giving a broad category, but those are application identification of some examples of application identification do. Now we also have schemes where you can put. Let's say you have an application which identifies whatever. You can service chain it through that. So send the packet to your application, and you can look at whatever you want, send it back. So that's also possible. So it's flexible in the sense that these are some of the inbuilt ones. So some customers have their own needs of whatever application they want to run, and it's simply we just hook it up and then it just runs as a plugin. So those are the examples.
I do have one more question about the actual encryption side of this.
Yes, we haven't got sure.
Are you going to talk about that later about what the encryption
Yeah.
How is that managed? How do you manage? The idea is it PSK? Is it certificate based? If it's certificate based, how do you manage certificates? What is that process for encrypting the payload of the data? How do we make sure that that's consistent across the board?
Right. Yes. So I'm coming to that. So
if you're going to cover it later, that's fine.
No, I was not going into the details of. But let's go to that. Anyway, it's security.
I have a question on this slide before we move on.
Yeah.
Do I understand that there are other routers in each of those clouds? Standard routers?
Non-120, yeah.
Yep.
There can be any number of non-120 routers.
And in between clouds then, from say edge to WAN or whatever?
Yes.
Do we not have IP reachability from the, say, router 1 to router 3?
Router 1 to router 3. You can have. In this particular case, it's just hop by hop because it doesn't have, it has to go through another 120 because they are the edge. But you could directly go. Yeah, I don't know why it's not showing, but absolutely. So if you have a connection directly here, you'll have two hops. One, a direct hop here and a hop this way. Now, what happens is once you come to the next set of step, you'll see that we will be calculating the best path to go there. So it's possible that even if you have a direct connection here, the SLA may be better to go this way.
Just because of what you observe in terms of the performance of the underlay.
Exactly.
So is there, other than possibly forcing unnatural paths, is there a benefit to having a state in all those intermediate routers? Or would I just want to pass the packet directly from router 1 to router 6?
Oh, if you have a direct connection here?
Well, many hops, obviously. But
Yeah. Are you saying that, let's say there are traditional routers there, you peer with it, just send it through the traditional routers and send it? Is that
well, earlier you said, and you've got state here, and you've got state here, and you've got state here, and I don't understand how am I benefiting from the state and those intermediate hops?
Okay. So how the state helps us with path failures and policy assignments. So let's say you have states here, and suddenly this link goes down, and this is like a one link case. I mean, this is going there. But let's say you have a connection, like you said earlier, to this guy. On a per session basis, you can fail over the path. For instance, you have let's say you have voice calls, and you have, let's say, TCP 80, and you can't drop a voice call, let's say, and you have a very poor link, a poor connection between this somehow, but you want to still use it. So let's say this path goes down. You'll try to cut over all of that to this poor link, only the voice sessions, nothing else. So now you see the session state helps, because how do you define the session? It's on a per protocol, port, and IP address, and that's why it helps.
I see.
Because on a per session basis, you can make policy routing, which is powerful.
So help us understand, how do you set up a tenant that establishes, I have a soft phone on my phone.
Right.
It establishes a TLS connection with another soft phone on the far end. How do I set up a tenant and a service to allow to dictate the policy of how I want to define jitter, et cetera, if you guys can't have no insight into the actual service because it's all encrypted?
Right. So in your case, let's say you're setting up a TLS connection. You create a. So at the end of the day, you're going to a destination IP.
Right.
So you have the final, not the intermediate destination IP, the final destination. I mean, think of it like you're talking from one LAN to another LAN. At the end of the day, that's what it is. The SD-WAN is like all these fancy stuff connecting them. But so let's say you're going from your source 1.1.1 to your destination 2.2.2. And your port, I'm calling it 443 for now. So you define a service called 2.2.2, protocol TCP, port 443. That's your service to access. Now, whom do you want to give it access to? Your tenants. Let's say you just want to give it to engineering department, not finance department. So you define, one option is you can create two VLANs and have one VLAN give hold to engineering, another VLAN completely to finance, and simply put the tenant on that VLAN saying engineering. And then in the service, you give the access policy engineering. So if you go back to what I was saying earlier, what happens is packet comes on that VLAN, it gets classified as engineering tenant, the broader tenancy. It goes in, it hits the FIB, which has 443 and the IP address. So that gives you the service. Then you go to the access policy. It says allow engineering.
So what happens when the service is a peer-to-peer video app, and I want to guarantee jitter for that video app?
Yeah.
But if there's FTP file transfer from the same two nodes,
yes,
I could care less about
yes,
those two services.
Right. So that's where you have two services now. So a service for the video has a different port and protocol.
But what if it's TLS? What if it's encrypted? I can't.
It's still unknown.
Right.
It's still a different port, right? For example, let's say it's TLS, it's 443.
Well, let's say all traffic from my two engineering endpoints,
right,
all 443,
okay,
different applications.
Okay. So you're going, but what about the IP? I mean, at the end of the day.
So from my engineering workstation to another engineering, we're collaborating.
Yes.
We're in Office 365, and
right,
I'm sending him a large file for him to do some analysis off of, and at the same time, we're video chatting as we're having the conversation.
Sure, sure.
All of that is 443 from one workstation to another workstation. And
yes. But is it the same IP destination too?
Yeah, same IP.
Okay.
It's peer-to-peer communication.
That's okay. So here you're talking about overlapping IPs. That is, in the sense, you have service A, 1.1.1, port 443, service B, 1.1.1, port 443.
Right.
But where it finally goes to will be different, correct? That you agree?
No, it's the same, because I'm collaborating with another engineer.
Okay.
You're using the same certificates, effectively a tunnel, you're saying? So basically a VPN?
So, yeah.
No, not even, it's two, it's an application. So let's say I'm doing Slack, not Slack. What's a peer-to-peer, because Slack is a horrible example. I'm doing an IP phone. I have an IP phone that does TLS between the two endpoints, just point to point. There is no controller in the middle. Maybe there's something that sets up the session between the two, but other than that, it's peer-to-peer communication. And then I'm using SFTP to transfer files at the same time.
Sure.
And they all use 443, so it's point to point. I want to guarantee the voice traffic, but I could care less about the SFTP traffic.
Right, but so again, it's the same IP, same port, same port.
Right.
But how are the application figuring that out at your final end then?
So then, obviously, when I'm setting up the connection between the IP phone, I'm going to, it'll be 443 with some funny, port or whatever. I don't know.
That's the thing. So at the end of the day, even if you're doing all this, your final application should have a unique IP
so
port.
the port itself is, I can use that port.
Exactly. That's the answer. That's exactly the answer. So
basic network.
So literally, what you explained is what tunnels do. So literally, that's exactly what tunnels do. You create one tunnel and shove everything into it, and it comes out the other way, right? That's exactly why we are different, because we separate that out. So when you define an application, the first question is how does your application? So we look from an app. That's why it's application centric. That's why all of our questions will be what port and socket does it live on? Okay, so 443, the other one can't be the same thing because you can't have the two things.
Because it can't, the application.
Exactly. So that separates out. That becomes the service.
Okay.
That's exactly what it is. You create an application, you create a service, give access to tenants, you are in.
Okay.
So a lot of what you're talking about in terms of creating a service and understanding who has access to it probably already exists in most of your customers and their firewalls.
Yes.
Do you have a way to map those firewall controls into your system, or is it still, I've got to rethink this for 128?
So, for example, in one of our customer network, it was Cisco. So Cisco had access list, which is like a firewall. So what we did was we literally wrote a script which converts a Cisco configuration into our configuration. Now, the difference is you can slice and dice it like 10 different ways, however you want. For example, in that Cisco config, it had like 10.1, access 10.1, access 10.2, access 10.3. It's like you have like it's like a whole page long. So we created all these stuff and told them, this doesn't make sense. Can you say /24? Yeah. So they said, yeah. We were just adding it willy-nilly kind of thing. So yeah, that's what. So that's an example. So we took a Cisco config, we ran a script and created the services and presented. These are like 4 different ways we can create a service, and they were happy with that. So that's an example. So similar. I mean, we don't have it for every single firewall out there, but at the end of the day, if the firewall can dump something, it's simple for us to convert it into it. So that's exactly how we do. Any other questions?
I don't know that we ever got to the encryption question.
No, I haven't. Okay, so let's go to the encryption question. Encryption, so there are a few things. Okay, let's go to how we encrypt it. We encrypt the payload and we encrypt the metadata too. And A is 256. Or A is 128. You can use either one of them. You can choose one of them. A is 256 is, of course, very secure. So that's what we use by default. Now, how are the keys distributed? I think that's mainly a question. It's not certificate based. It's literally the keys are distributed. So we have a security key manager which generates these keys, and they distribute it to all the routers. And when he initially started, just to make it work, it was part of the config. It's no longer there. Right now, it's just the security name is part of the config. But the keys are randomly generated and distributed to all the routers in a secure way. So this way, what happens is none of these keys can be really learned because it's really in the process memory. It's not dumped anywhere. It's not accessible anywhere. So even if you hack it is in the processor memory. So if you're in a root and then try to figure out the process, maybe you'll get it. But it's just not possible.
Right, it's not easy.
It's not, it's virtually impossible, but yeah. So that's where it is. So literally, we generate the keys and we distribute all the routers. And let's say you create a security key called web security, which you want to apply to, let's say, all web-related services, maybe. Then we will create a key and distribute it to all the routers. So now they know what that web security means. So that's how we do it.
Are you doing rotation of those keys?
Yeah, so it's like a rekey. There's a rekey mechanism with which if you turn on rekey, then like periodically we can.
Based on the timer.
based on
Yeah, I'm assuming there's a default timer. Is that something that an operator can choose?
Yes,
choose
yes.
if they want to rekey
Yes,
at a
exactly.
different interval?
Right, yeah.
Can we use like an external key management system that you guys can tie into, or is this just?
So right now it's what we generate, but it's easy enough to integrate with an external key management. But at the end of the day, it'll be like a script we can call, and you can fetch it and come in. You just have to make sure the external key manager connection is secure. That's all. At the end of the day, if it's secure, then we should be fine. Yeah.
Do all the routers in the path need to know those keys, or just the ingress and the egress routers?
So that it has no. I was coming to that. You actually went to the next point because that's an important piece of this technology. Because consider any encryption or tunnel stuff. Let's say if it's a point-to-point, right? What happens? Comes out, decrypts it, encrypts it, comes out, decrypts it, encrypts it, comes out, decrypts it. We don't do that. Only the ingress encrypts it, and then everything is a pass-through, and then finally it comes here. And then he only decrypts it. So the ingress encrypts it, the last egress decrypts it. So that's the beauty of this. So why, if one tunnel discussion will come later, but that's one distinction you have to understand. Tunnel or no tunnel doesn't matter. When you have a point-to-point link and you have multiple point-to-point links, all they know is there are a bunch of packets coming here. Let me decrypt it, apply the next access policy. That's also the thing. No access policies are again applied because it's already done on the ingress. Right. Because firewall is letting you through. That's a network, right? And encryption only at the ingress. So that, from performance perspective or from management perspective, everything that is the unique factor which we have, which none of the others have. Because you can do it with tunnels too. Say, then it'll be an n-square problem, right? You'll have to create like a full mesh at the end of the day.
So what about the metadata? Because you said the metadata then is inspected along the path, but you said the metadata is encrypted. Is that unique in that gets decrypted at each hop along the way?
Yes, the metadata, absolutely. The metadata gets authenticated and decrypted at each path because we need to know what the contents are.
Right.
But that's only for the first packet.
Right.
So once that's done, you're done. So it's not a problem, right? But just to continue on that, why the other routers need to know about it, you never know that there could be a local session starting from here and ending on this guy. You don't know that. Because it's possible that you may want to go locally from router 1 to router. Though there are hops sitting out there, it's perfectly, maybe it's for a ping utility. I don't know. It is for logging in to figure out. So all those have to be secure. So we can't assume anything. But otherwise, you're absolutely right. That's true. You don't need to know it. But it's a generic architecture, so we just push it down. But we could make assumptions if we want.
Everybody gets the keys then?
Yes, everyone gets the keys. Because you could change that policy any time to do whatever. So that's why we push it everywhere.
Is the security key manager function part of the conductor?
Yes, it's part of the conductor.
We've heard a few times about low overhead, no overhead advantages.
Yep.
Doesn't your use of AES suggest that you're going to have to do some buffer padding?
There is a padding, that's true, because if you don't come to the full alignment, you will have to pad it up. That's there with the encryption, yes. But I think any encryption, blocked encryption you use, the good part of you using block encryption, which is efficient rather than like, but unfortunately that's part of the block encryption. So that small overhead will be there. You're absolutely right.
The initialization vector is same as anyone else's.
Yep.
Yeah, the IV is the same, but you're right.
For an intermediate packet, then I mean that might push you over a frame size sometimes.
It could a little, but we have fabric fragmentation. So, for the most part, what we see is that doesn't kick in. It's like less than 1,000. I think the packets being sent are like 1,300, 1,400. So we are at the edge. It's okay. But yes, if it's a big voice or video coming in,
this is the difference between nothing extra or what, 15 bytes?
Yeah, pretty much. Yeah, exactly. It'll be 16 bytes. So based on, it'll be, if there's something, then we add the remaining. So that's the padding you add. Absolutely. Yes. So have I answered the question for the security or a security question?
Yeah, that was exactly what I was looking for.
Okay,
Thank you.
Yes. So I think two session awareness is there, but two important factors to understand is like the firewall features are done on the ingress. Any identification, any service, any policies are done on the ingress just once. and the remaining routers trust it, and you can take it. So you don't take the extra hit on any other router, even for the first packet or subsequent packet. Second, the security, which you brought up rightfully. So again, the first router does it. Yes, the first packet metadata needs to be encrypted, decrypted, but otherwise it'll be just going through as is. That's one thing which makes us different from any other technology. Two things actually, which makes us different from other technologies. There are many, but okay.
And is there any kind of, you're doing a lot on that first packet?
We do a lot, yeah.
Is there any kind of like buffering mechanism or something that is going to keep it there while you do all the lookups and encryption?
Oh, no, sorry. When I said it a lot, I mean, not that much, but so how it works is most of the determination is made at the fast path, most of it, because again, find the tenancy. It's a LPM lookup. Then once you have the tenant, you look up using the tenant, the IP and the port, another fib lookup. So that's also the fast path. You find the service. Then using the source IP, you look at the access policy. So once it's all done, so now you already figured out the service, you figured out the tenancy, everything is there. So once you come up, all you have to do is set up the sessions and with the right policies, which will be associated with the service anyway. So there's not much processing happening there. Yes, it goes to the fast path because we want slow path because fast path is doing what it needs to. Otherwise, it just sets up the session and the policies, which is already determined when we did the lookup. So there's not many lookups we have to do from that perspective. Okay, I think, this is what's happening under the hoods. Well, we kind of went through it, so detect a new session, that is a packet came in. Yes, associate tenants and services, we talked about it. First, you hit a source lookup table, figure out what the tenant is based on your network or on the interface. Then you go hit a fib table, you figure out what the services are available to that tenant, and then you hit an access policy to make sure these tenants have access to it. So then what we do is we preserve the original IP addresses in the metadata, which is what we are carrying, and that's our session key. The 5 tuples plus the tenant information forms a session key across all. So for example, if you have same IPs on two, I was coming to that example. If you have same IPs on two services, for whatever reason, because you get natted at the final end, you can do that, but with different tenants. Because that's because an IP port protocol, if it's the same set, what distinguishes them will be the tenancy at that point. So you could have the same thing hosted at 2 different VLANs and your other data center, but 2 different tenants accessing it. So it's perfectly fine because we will create a unique session for them, a unique flow for them, so they won't collide. And it's easy to manage them instead of creating all these access policy rules for that. So the metadata is put in. Then, so we preserve the original address in the metadata, and then we put the waypoint address. So the waypoint is simply the source IP of the originator and the destination IP of the destination router. That's pretty much it. It's very simple. How do I go from router A to router B? You use your source IP and you use his destination IP. It's as simple as that. That's all what it is. That's all routing should have been. Unfortunately, it is not. That's all what we're trying to do. I mean, I'm not saying, let's say you're creating a tunnel. They are doing the same thing. It's like source IP, destination is the same thing. But at the end of the day, we are having separate session. We create a waypoint. When I say the waypoint, there's a wayport also. Waypoint is a combination of 4 things. It has the IP address, source IP, dest IP, source port, dest port. So the trick there is, which actually he came up with, the trick there is you have the high port, 16K to 65K, and you can have like 50K source ports, 50K dest port combination. You have almost 2 billion combinations. So from one source to the other source, if you're even leaving 16K ports away and only using the high ports, you have 2 billion combinations of flows you can from one place to the other place. So if you have 2 billion combination of flows where you can have different DSCP bit marking if you want, you can have different policies you can do. Why send it through like one set of ports and IPs? That's pretty much what the technology does.
In a basic deployment, if you had 128 routers distributed throughout that cloud, would the the involved waypoints be just the two at the edge?
So,
or would we, under normal circumstances, still go click by click through?
So that really depends on whether the 120 router is in the same authority or not. For example, let's say these two, you've gone through authority. Authority is like a domain. Let's say you have two 120 routers defined in a domain. At that point, any 120 router communication is only through waypoints, because that's what we believe in. It's like, it's secure, it has all the properties, like secure vector routing. It's security, it's directional, and it's just normal routing. Now, let's say you had another.
I'm struggling with the mental model here.
Oh, sure.
I think I get it, but I would never build a Gre Tunnel this way. So I'm not quite there yet, but give me time.
Yeah, sure, definitely. Yeah. So let's say, why I was talking with authorities, let's say you had another authority here, which, let's say it's AT&T, is sitting out there, or a service provider, and we had no clue about it, let's say. Because you have 120 router, you have 120. There's an underlay, someone is doing it, and he's also using 120 router, just like Cisco routers anyway, 120 routers. In that case, SVR will be between these two routers, because we don't know anything about that router. But the moment we peer with them, if they become our adjacency in our terms, like in the traditional world, you'll say, okay, it's a BGP neighbor or a neighbor. In our case, we say it's our adjacent router. If it becomes a peer, 120 peer somehow, then yes, we will use waypoints. So now, just to, in a Gre tunnel, for example, you would create from this end to this end, right? And if you have multiple ones there, you don't care. You only care the destination.
The ends. Yeah.
Ends. The difference there is, let's say you have 5 of them. It becomes an n-square problem if you really want to go all of them, right? Because you need a full mesh. Here, it's not an n-square problem because it's just IP reachability at the end of the day.
Well, and you're keeping state on flows regardless.
It is.
So however many flows there are, that's how much state you have.
Yes,
it
but
doesn't matter how many peers there are.
Right, but if you look at from the maintainability perspective, even if you have 5 routers here, irrespective, that's how we work. So if a router works the way, it's a session-oriented router, that's how we work. It doesn't matter what happens, we create session state. So the n-square problem doesn't really exist there because you're just doing IP forwarding at the end of the day. For us, it's an IP packet. We don't know it's because of n hops it's coming or 1 hop it's coming. It's a packet coming to us. Has it gone through all the metadata? Does it have metadata? Great. That means, and can I really decrypt it and authenticate it? That means someone at the ingress side has made the decision that it's valid, and we continue to create the sessions and pass on. Yeah, go ahead.
Just to be clear, though, because I think you maybe going back to a question you asked earlier as well. If you want, actually, I think I have I do have a mic, right? Okay. If you want direct bypass from an ingress to an egress without going through any 128Ts in the middle, right? And you just want a 128T, 120T, you can absolutely do that. That's just the policies that you've configured for routing, right? Just like as long as they have reachability over IP, of course they can talk direct.
Sure.
It happens that a lot of our customers don't want it to go direct. So they want branch-to-branch traffic, for example, frequently to go through their data center, even though from an internet perspective or IP perspective, they could absolutely just send it directly from branch to branch.
Yeah.
And so we allow them to have those policies so that they can force traffic to flow however they wish. And typically it's because they want it to go across, either MPLS network or some sort of backbone that they control, or maybe they want it to go through some boxes that monitor their traffic or whatever it is, whatever their reasonings are. But they can force it however they wish.
Gotcha. Yeah, I'm not making the case that I want one or the other. Just trying to understand your model and the idea that you would do waypoint to waypoint to waypoint, many hops. Taking advantage of that feature at every point. Mm-hmm. That was not intuitive to me.
Gotcha.
But I'm getting
sure.
Yeah. Thanks.
Question on fast path versus slow path.
Yep.
I thought these were x86 boxes, so what are we talking about when we say fast path?
It's relatively slow, relatively fast. Everything is relative, right? So, yeah. So, well, it's the difference is you can pin threads. You can pin cores for fast lane. For example, you can have coreless where your fast path runs as coreless, where Linux scheduling will take care of it. In some cases, you don't have that much traffic, you can use it. Or you can really pin cores for fast path processing. When you do that, all it's doing is just fast path processing, right? Because you need a throughput. If you really need, let's say, I want line rate, if you're saying that. So we really need to make it work. And so make it work really fast. And the slow path, all it has to do is set up the sessions and send up. It's not doing a lot, but it's just
an extra step.
It's an extra step it has to do. So what we do is we just ship it off, and because most of the packets have to be forwarded in the fast path because you've already set up the flows, and then the remaining packets the other ones are first packets coming in. If you have like a lot of first packets coming, yes, it may not have enough to do, but at the same time you're shipping it up, and once it's injected, fast path is still sending the packet out. So even if we go to the slow path, it's just setting up the context and sending it out. Now it's it's not like let's say if you take any other routers, you have like some routers have interrupt path. You have fast path, interrupt path, and then you have the slow path. It's nothing like that. All this is doing is why we are calling it, we call it service area. It's relatively slow. All it's doing is taking a packet and setting up the session table and injecting it back. That's all what it is. So when it's injected back, who picks it up? The fast path picks it up.
Typically, if I deploy one of these boxes, then am I installing 128T onto bare metal?
You can, yeah, yes.
I can. So in other words, I don't have to. But
you don't have to.
If there's a performance concern, maybe that's what I want to do?
Yes, yes. And then you'll get the full performance there. And you can also do a PCI pass-through if you have a VM. And if it can actually keep up the VM, then yes. Yeah. So it's at the end of the day, it's there's no magic. There's like scheduling. So you give the thread completely to a core. So one thread runs on one core, then it gets a maximum performance. So we have not changed anything there. We just, so it's up to, so for example, there are cases where you can put 3 cores to it. And why, again, that's going to Intel DPDK mostly because we don't have copies. Even when you go to fast path, there's no slow path, there's no copies. We literally take the exact same buffer, and that's linked, it's shared memory. So it works on that packet information. So we don't have to manipulate the packet there at all, because as I said, all it's doing is taking the packet metadata information, creating the session table, and injecting it back. So the packet is hanging the same place everywhere. So that's why it's fast too. Okay, so the waypoints, we talked about the 4 things: the IP address, source IP, desk IP, the source port, desk port, which are going to be a combination of them. You have 2 billion combinations, so with one set of IPs, and you can have more. Then essentially this is nothing but saying that you apply the access policy, the security, and finally send the packet out. At the egress end, what we do is we have to decrypt the packet and send the packet to the destination. So that's pretty much it. Again, the 2 important factors are any access policies, any firewall decisions are made at the ingress side only, and the ingress side sends it. So we don't have to make this decision at every point. That's number 1. Number 2, encryption, again, is only done on the ingress side. So you can just pass it through, and only at the decryption, at the final side, you have to do it. Now, this is...
One thing, sorry, Abhilash.
Yeah.
One thing I did want to mention on that previous slide. Okay. When we're talking about the waypoint addresses and ports, one of the reasons we focus on that is because unlike a tunnel in between, even routers that are in between, like Cisco's or whatever, won't treat it as a single flow because we're using different source desk ports, 5 tuples for every single one of those little flows. So if you're going across, for example, ECMP paths or link aggregation or anything that does any sort of hashing based on flow information from traditional routers or even Ethernet switches, they'll treat our flows as a bunch of discrete separate flows, and you can get much higher throughput bandwidth. Whereas if you usually go through a tunnel, that's one big elephant flow for devices in between, and they usually throttle that bandwidth quite a bit because you're only going across one of those ECMP paths.
That's a good point. You just have to make sure your hashing is down to the port level.
Of course, yep.
It's like an elephant flow versus...
Right.
A tunnel becomes an elephant flow problem.
Right. We're keeping a lot of mice.
Right. Yeah, it's like we're creating mice. Yeah, that's right. Okay. So this is again just to make it clear what we are doing. We are not adding any header. It's just natting the packet. So the ports are from 16K to 65K. That's why it's 50K combinations. We're just simply natting the packet here, and the original ones are kept in the metadata here. Now, these are the benefits. We talked about security. We talked about direction. Now, the directionality is very important from a fact that not only from a service perspective, even from a waypoint perspective, the directionality is there. Meaning, when a router 1 talks to router 2. Router 1 allocates a waypoints and sends it to router 2. And when router 2 is trying to send packets originating from router 2 to router 1, router 2 was the one allocating the waypoints, not router 1. So the scheme with which we allocate it, like even odd scheme, we've come up with different schemes, but that directionality is important to who allocates it. The one who's sending out allocates it and sends it. So he just creates a flow for that. So that's why it's directional too. So the way I send the packet to the other router is not the same set of ports with which the other router is going to send it to me. And hence collisions are not there. Because otherwise what happens is same source, same source IP, dest IP, right? If you really think about it, there could be collisions. So the usually question I get is, okay, that's great, but why don't they collide? Because the scheme we have makes sure that they don't collide, even with 2 billion options. And that's the trick. It's like the even and odd scheme helps us not to have collisions. And that's where the directionality is important too. I go to you, and you come to me. The even, local, odd, remote. That's the scheme which we use pretty much.
We had acknowledged the fact that a unique ports get assigned to each flow. How does the originating router learn about what the new destination port is for that flow? Is that sent back in the first packet on the way back?
Oh, you don't. You allocate it. So.
It's allocated at the source.
That's why I was stressing that. Yeah.
How do you know which are available and not already in use by something else?
So the source router tracks that. In the sense, when the session goes away, we release that ports back.
So I guess I'm still not understanding this. So I have my source router, my destination router.
Yes.
Packet goes across.
Yes.
It's going to be a unique port on the destination router, which is what determines
unique odd port.
Unique odd port.
Right.
Which he will never use as a source port on his side because.
Understood. But if I have router C that's also sending to the same destination.
Because IP is different.
Different IP.
Different IP.
Different source IP.
So that's the difference.
So different 5 tuple.
Makes sense. Light bulb.
We need any part of that 5 tuple to be a discriminator. One has to serve as a discriminator.
So you have the entire port range for every IP to IP combination.
Exactly.
That makes sense.
So that's the thing. We just made it. We were like we want to make sure it doesn't higher ports are used. So yeah, you can configure to say I don't care. The others are not there. You can change it to 1024 to 65535. You can. But we said okay, let's leave them for the others. And then,
that's super efficient.
Yeah. Right. I said the question of collision never comes into play from that perspective.
Between any two waypoints on the internet, you guys wind up exercising the transport port space quite a bit.
Yes.
What sort of funny things have come out?
When you mean you're talking about
what surprises have we learned?
Yeah. So, I mean, you're going to exercise, all ECMP.
Yeah, we found some funny things with NAT.
And you're gonna find, I don't know, maybe traffic is being, on certain port numbers is being, snarfed up by a something that slows you down, or
we've seen that.
Like, what kind of weird things happen? How can you tell that it's weird? Not necessarily between two endpoints or waypoints, but just on that port.
Just that port number. Yeah.
Or that
that's because of the session.
I mean, I know you can certainly observe the difference, but
right.
Are you able to determine that?
So
that just happens to one flow.
Yes,
and not a different flow.
Exactly. So one of the examples I can give is TCP. We were seeing that ACK problem, right?
Yeah.
So it was I'm not sure which carrier it was. So
well, we won't name
it. So. We were getting this weird packet after the session was closed, I think. Even after the session was closed, we were getting an ACK packet. We were literally getting ACK packet from this guy.
5 minutes later?
Yeah, 5 minutes later. It didn't make any sense. So they were saying, okay, the flow is there, things are not working. So we were trying to understand we cut over the next transport, it worked. I mean, it wasn't a problem. So, but we found out for this particular set of flows, we were getting an ACK even after the TCP has really closed. But we have a TCP state machine. Mm-hmm. So that's why the per session thing helps, because we could pinpoint which exact session was running into it and why that, and the TCP ACK after a close went to an invalid state because it's an invalid transition. If you have fin-ACK, you go to invalid transition. Done, yeah. So that's where it helps. So now you can pinpoint a session and say, hey, this is not working. So let's say a customer says, my service, web service is not working. And you've really granulated it to a particular application. And said, mine works, his doesn't work. We're going to the same place. Great. What is the difference? What's your source IP? Just put it in, you are able to directly get what happened to that session. What are the TCP state transitions, if at all, or what are the counts, packet counts. So you can say, okay, the packet's actually going out, nothing is coming back. So on the other router, it's getting in, nothing is coming back. So maybe someone has blocked it for that particular session. So at every router, this is why the session helps. You can know where the packet got dropped, why it got dropped. I mean, which at the transport layer,
Do you respond to weirdness in the underlay like that? I mean, I imagine, port 31337 might give you funny results, for example, right?
No, so the TCP state machine does some checks, which you can relax also if you want, but we don't, we just drop the packet if it's really invalid, but we don't really respond to anything. There are some other features where we have to, if there's a very bad link with TCP, we make sure we retransmit. But that's a feature we turn on. For example, VSAT links, right? It's very bad. So we'll have to retransmit the TCP. So we cache and retransmit it. So there's something called session optimization, which can be in a separate session. We can discuss that. But
we don't change the ports or stop using ports automatically like that just because of that.
I mean,
except for when we detect their NAT firewalls in between our routers, that's a slightly different topic. But and we have a discovery feature to do that and everything else. But in terms of what you're asking, no, if there's some funny business on port 1337 or whatever, we don't just automatically determine it. But if you can set us to avoid those ports.
Gotcha.
Another example is the UDP Transform. So that's again unique to 128p.
That's true.
So what we do is if the TCP, there are like some firewalls in between which doesn't like these metadata stuff. So usually people ask, okay, what if this firewalls stop you? The good part is we figure that out because maybe it's an ACK packet or even a SYN packet with metadata, ACK packets, any packets, we detect that. And then what we do is we UDP transform the packet. Now what we mean by UDP transforms, literally it's transforming into the TCP header is changed to UDP header, that's all. Nothing else is touched. So it goes as a UDP packet and it's happy, it gets the other side and we will send it out. So if you're asking, have you seen issues? We have seen issues, and that's why we had to implement that. We've seen issues where some firewalls were not happy that we were sending these, especially on path failures. For example, let's say I've established everything is great. Now let's say this path fails. We have dynamic path failure. So let's say there are two paths here. Let's say there are two paths, P1 and P2. Let's say there are two paths here. Let's say path 1 goes down or is below SLA. What we do is we detect that and fail over the path to the packets to the second path. Now, when that happens, if it's a mid-flow TCP, it's possible that some firewalls, because now how that happens is it's important that we send metadata with it. So first packet metadata is not only for the first ever packet, but if a path changes, how does this guy know that's a different path? Because we are using a different waypoint transport, right? Like you are saying that this is WP1, WP2. We may be using WP2 to get here. Right? So the IP has changed, so he has no clue, so we turn on metadata. Now you have a TCP ACK packet with all these beautiful sequence numbers, and suddenly this metadata is here, and the firewall see what's going on. It's like the size doesn't match and can drop it. So we have something called Firewall Detector, which we run periodically and figure out from the paths if this can happen, because we send all these type of packets and figure out initially, once a path comes up, we'll figure out, okay, is this possible to send such packets there. If not, we will use something called UDP Transfer. That is, we will get this packet, we'll simply change the UDP header. And the good part is, for each protocol, now the 2 billion combinations per protocol. So we're not going to run out of ports. So you can create, for UDP also, they're the same combinations, and we send it out.
Is the detection happening with the BFD?
No, it's called Firewall Detector. We actually send TCP packets between 120T routers.
So it's its own synthetic transaction that you're doing just to see what's going on.
Right. So we send SYN, we send ACK packets, we send different combination of packets with metadata, without metadata to make sure does the other guy get it and he's able to act back. So if that's possible, then we know there's no firewall. So there's a bunch of combinations we run on this to figure that out.
How often does that happen? Is it just at link setup that you send a bunch to figure that out and then wait for a change?
It's configurable.
Yeah, it's configurable.
Oh, it's configurable.
Yeah. So if you want to run it, initially we were running like every minute. It was crazy at that point. So we just made it.
That's probably a bit too much, right?
Yeah. It's like, what is going on? So he was like saying, okay, I've seen all these TCP packets. So we are TCP packets. Actually, those were the funny packets. packets you'll see in the network, because we have to send those funny packets to figure out the network is bad.
Is that configurable based on metrics? So, for example, if you suddenly start to see higher packet loss or higher jitter or something along those lines?
Right now it's just a hard number, but yes, we could make it reactive, but people haven't asked for it because usually the CGNs which change, etc., may not be that much. So we have a number which we put, it's just a timeout number.
Gotcha.
So you could put it an hour or half an hour, however you want. Or people put it for a day because they don't expect network to change that much. Maybe Friday you can change it up. Something.
Okay.
The first packet in a TCP flow, the encrypted one, does it look like a TCP SYN with a payload?
That's right.
Okay, so that's the firewall problem, isn't it?
Yes.
Oh my God, what's that?
Yes, right.
Some firewalls and also
Some fire.
and also the path failure, an ACK. Because the sequence number, right? That's the thing. That's why we have to do because either you have to do a proxy, TCP proxy, or do this. This works much better than creating a proxy and creating states for the proxy. So yeah, that's the other case. So you path failover, you go with an ACK, and then you're done with that. So
Talking about path conditions, what happens if waypoint 2 fails?
okay, so if both paths fail.
If waypoint 2 fails,
the whole system,
the second, the 128T at the other end.
So you're saying, I'm sorry.
You mean in that scenario where there's just two routers peering with each other and they only have that one path?
No, just if you're talking about, I've got my source waypoint 1 and waypoint 2 is the egress where all the decryption and stuff is happening. What happens if waypoint 2 fails?
You mean the IP reachability is not there?
Yes.
At that point, that's the only path you have, right? If you have a secondary path, we'll fail over. At that point, our BFD session will go down because it's not reachable. And we'll say it's just not reachable at that point.
Okay, so you'll restart and look for another way.
If we will look for it.
If the configuration allows for other potential routing paths, it will
fail over there.
Oh, sorry. Yeah, if the configuration, if there's other paths configured to be available with a higher priority or lower priority, I guess, then it will advance through those options. If there's no other options, it will fail.
Okay. So obviously, if I'm doing NAT capability between the waypoints, between the two peer devices, and I have another path, but the other path isn't a path that I can share, create a waypoint peering relationship with, that other path is so important me to make sure that it's secure, because I can't the conductor and all that isn't setting up any type of special connectivity between that.
Right. So a typical example would be, like, let's say in some cases people use MPLS in some cases, or some private network, they have a private network. Then you use SVR for broadband, LTE, everything, and the private network, you could use SVR, you could directly send it to it. But with SVR, the good part is you'll get the session orientation, otherwise you won't get the exact same session orientation. Because when a packet, now you have to make sure your network works well, because when a packet comes to the second router through your means, you are losing the session orientation because you're source natting the packet, right? So you lose that second. That's why the SVR is important even in the private. You can do it, but you won't get the same benefits that SVR gives you.
So eventually the path to displacing the thousands of routers is that as I trust Waypoint more and more, my concern isn't necessarily the Waypoint going down. I'll just add redundancy and I'll just make a bigger, more redundant box.
Sure. Yes, that's right. That's right. Because usually the head-ends have multiple IPs and distribute across, so they can reach. This is just a quick layout of the metadata. So just to show that deep dive, saying this is a metadata cookie. The question is, how do you know it's a metadata packet? We talk about all this metadata. That's because there's a metadata cookie signature we put in there. That's how we detect that it's a metadata packet. Then there are metadata flags which are unencrypted. This is because metadata just opens up a lot of other possibilities, like turning off metadata, turning on metadata. Because when a path goes down, there are cases where you may have to have the first packet go to a different site. So the unencrypted portion helps because you don't have to run decryption on that. These are just flags on it. But authentication will still be there, so no one in the middle can really change it. And then the payload. Payload is what the actual contents are. Yeah, so I think what we talked about is simply SVR, which is the data plane. How our data plane works between two 120T routers. Now we're going to see how the data plane gets set up from the control plane perspective. But any questions on this?
What problem is the cookie solving?
Oh, detection. So how do you know?
Any port number, 16,000 to 65,000 on a 128 router is.
That's right.
I mean, so.
Yes. The destination port, definitely it is there. But this is so that there are two factors to it. One is to make sure that it's a valid 120T packet which we are sending. So we have the authentication on it, but it's possible that people can turn it off. The authentication can be turned. It's configurable to turn off. Because in some cases, people say, I don't care. It's my private network. Like he was saying, I don't care about authentication. So if you turn it off, we can't force them to turn it on for this. So we need a mechanism, even without encryption. If you're using a private network, when you're doing SVR, we want to find out what the metadata packet is. So the port itself is there, but let's say in that case, they're somehow sending, like you said, not SVR, but another one, but happen to be that port. We want to distinguish that from this. That is, for whatever reason, it's coming with a particular port for a different tenant. So that's the thing. Let's say you have a WAN interface, and you are coming from internet to access it. I'm just saying port 80, or port 16K. It shouldn't be, but let's say it's 16K. And you're also coming from the other side for 16K with metadata. At that point, you can't really distinguish one versus the other. The metadata cookie will indicate what the difference is. Because at that point, it's like a collision. Because you have to choose one versus the other, but the metadata cookie will indicate what it is. Because you can have other ports open on that same interface.
Got it.
So any questions on SVR? I think that's like the fundamental thing, what we do, which is different. I hope you understood why it's different. In certain cases, again, reiterating, everything's done on the ingress, then done at the egress, security again in ingress, the egress. We just use all those 2 billion combinations to route between ones. Failover as different IP, different set of ports. Policies, session awareness, it's directional, secure. So those are the important, secure vector routing encompasses all that.